video, I would like to continue what we already talked in previous session about designing a groundwater numerical model. Same as previous video, many of the pictures, plots, tables that you will see in this presentations are coming from the Spoke Applied Groundwater Modeling written by Mary Anderson and William Wisner. In previous video, we talked about two types of boundary that we have in groundwater modeling. The first one was the physical boundary, which technically defines the spatial domain of the groundwater model that we are looking at. Technically, it shows us how big the model is. And the second boundary condition or boundary is the hydraulic boundary condition, which technically controls how the outside world is talking with our groundwater system. You know that if, I don't know if it is right, but if it is the entire world, we would like to model a small piece of the system. So technically it is very important. So we are going to take this out, but we need to consider that this model is a part of a big world or bigger system, to be much more correct. So technically these hydraulic boundary conditions defines how the system talks with this outside world, which is actually very, very important and very, very difficult in so many cases. So a good model technically must have a good, reasonable, correct hydraulic boundary conditions. We talked about the hydraulic boundary condition. We said that mathematically there are three forms of boundary condition. The first type is the specified head boundary condition. The second one is known as type 2 or specified flow boundary or Neumann boundary condition. And the third type that we talked about was known as type 3 or head dependent boundary condition or Cauchy condition or mixed boundary condition. And we said that technically there is a formula or a main primary formula to calculate the head dependent boundary condition, which we denote by HDB boundary conditions as well. Okay, those were the things that we already talked in previous videos. Hydraulic boundary conditions, depending on where they are located, can also be classified into two perimeter boundary condition and internal boundary condition. So obviously, if the boundary condition is located at the perimeter of the model domain, we call it perimeter boundary condition, or if it's a sink and source term within inside the model, we call it an internal boundary conditions. For example, in this condition, and in the previous video, we said that, for example, here you can see that these red boundary conditions are perimeter boundary conditions, and internal boundary conditions are, for example, these three blue rivers or these two yellow wells. Okay, now I would like to specifically talk and discuss how we can find and define physical boundary conditions, which technically defines the size of the problem that we need to consider, and also learn how we can use these type 1, type 2, type 3 mathematical boundary conditions, or let's say mathematical expressions, to simulate the physical and hydraulic boundaries. Physical boundary conditions are usually defined or identified by doing some sort of field investigations, and they are usually obvious form of boundary conditions because they physically exist in the nature. But herein I would like to talk about some form or example of major physical boundary conditions that we as a groundwater modeler are looking for. The first physical boundary condition can be identified and located at geological units which have lower hydraulic boundary conditions. So for example, if this is a system, and if I know that for some reasons, for example, let's say this way, for example, if in my contract they wanted me to model the groundwater here in this space, so technically if I go and see that near to this area there's a hydrological unit which is almost impermeable, it is like a rock or bedrock or something like that, then there might be a good idea to extend the system and reach to this area and define this area as a physical boundary conditions. So if you go and think about what type of mathematical expression suits better to define this form of boundary condition, I mean type 1, type 2, type 3, type 2 and type 3, it is easy to answer this question. You know that actually type 1 was the specified head. Technically we went and we knew that, for example, what are the values of head at specific location. So this is not a good one for this one. Type 2, which is the specified flow, can be a good mathematical expressions to model this form of low hydraulic conductivity hydrological units, because you can define a no flow boundary conditions there. Okay, so where are these low hydrological units? These two pictures showed two examples that we can come up with. As you see here, for example, in this system, you see that for some reasons, some geological reasons, the bedrock, which has a very, very low hydraulic conductivity or almost zero hydraulic conductivity, outcrops to the surface and create a system like this. Okay, as you see, for example, if I want to model this system, technically I can define a no flow boundary condition here at the bottom of the system, for example, if I want to model this, or no flow boundary condition here in this area. Okay, so this is one example of how the low hydraulic conductivity hydrological units look like. This picture shows you that, for example, in this river that you see, technically this river flows on the bedrock. So these are the bedrock which are outcropped and creates a no flow boundary condition in the system in that area. As you know, 3D groundwater models look like this, and technically we need to go and find the boundary conditions at the bottom, at the top, and also at the sides of the system. Usually in the most models, and actually you're going to see later why it is the case in the next slides, usually the bottom of the groundwater systems, we consider, or we extend this system until vertically until we reach a reasonable no flow boundary condition or impermeable layer. So this is the rule of thumbs that we usually do in the Z direction, and usually if the hydraulic conductivity of this layer is almost 2 or 3 orders of magnitude less than the hydraulic conductivity of the aquifer system that we have there. For example, if this is, let's say that if this is 30 meter per day, if this is like, I don't know, like 3.3 or 0.3 meter per day, so this can be reasonably considered as a no flow boundary conditions. Okay, another form of common physical boundary condition is known as shear zones or faults. As you know, these are nothing but fractures which have happened due to geological forces. Technically, 2 layers are displaced and these cracks are created. So this is another thing that we usually are interested to look at, and we sometimes want to extend the groundwater models until we reach these boundary conditions. And usually sometimes, I mean there are so many scientists and researchers are interested in this physical geological events, let's say, and they are usually, I mean, and I've seen so many cases that actually groundwater modelers are very much fortunate to work on a well-studied fault, but you should be very careful because although you may know where these faults are located, but it is sometimes difficult to know how these shears respond hydraulically. So in some cases, as you see, for example, here, if this is one layer and we actually it has been displaced like this, and if this is the for example an shallow aquifer, and if the groundwater reaches here, so there are 3 possibilities here. So they may reach a very conductive system. This might be like an open pipe system which can easily transport water, or it may be a very low hydraulic conductivity system which may act like a barrier actually here, or even in some cases, although there's a shear there, we don't see that much difference between the hydraulic conductivity or hydraulic conductance of the system in that area. But this is definitely something that can be considered as a physical boundary condition, which would impact the size of the model. But again, there are so many different opportunities here. For example, in this figure, actually it seems that actually the groundwater moves like this, but this is an impermeable layer which can be modeled as a no-flow boundary condition, and actually it forces the water to go up and creates a spring here, okay, which at which actually the head is 0, right? So this is a definition of the atmospheric pressure. So there are so many opportunities or possibilities in the this interesting geological units that we need to look at. So again, if I want to repeat, that would lead to a no-flow boundary condition like this, or I don't know, a constant boundary condition like springs, or lead to a pipe type situation that we need to think about it and work on it and come up with a best boundary conditions to represent the real world. So here are two examples of the shears that we can see and we can find in nature. I found these two pictures from this paper. As you see here, for example, the layers have been displaced and shifted such a way that you see different huge differences between the left and right hand side of the system. This is, for example, is another case where this big layer has been outcropped into the surface, and as you can expect, this system has been continued into the system in the deep layers. Another common form of physical boundary conditions that we as a groundwater modeler want to look at is known as a surface water body. Surface water bodies can be an ocean, sea, or large lake or stream. Technically, we like these water bodies, as you see, for example, here, the lake or sea here and a stream here. So we like, and we would like to extend our groundwater model to reach these spaces, because usually we know that we have enough information about what's going on hydraulically, specifically the stage of the stream or the sea level, and we know that usually it is independent of the smallest and slowest hydraulic responses of the groundwater system. For example, I know that if I put 10 pumping wells here, I know that it doesn't matter how hard I'm pumping, essentially it is almost impossible to change the sea level, right? So this is the condition that's why we usually like surface water bodies to be at the border or at the boundary conditions of our conceptual model or numerical model. And as you can guess, type 1, at which we know or we specify the head condition is a proper boundary conditions to usually to model the physical boundary condition, but this is not the only one. Actually, the type 3 is another alternative to represent the lakes or streams in many groundwater cases that we are going to talk about this later on. Okay, I think now it's the best time and best place to talk about a few important things that we need to learn in doing groundwater modeling. As you know, the streams are not fully penetrated into the aquifers or the unconfined systems, or even in some cases the confined systems. For example, if I want to draw, if this is my river, and we solved a few examples, right, in the homework. So my river would be penetrated into the confined system like this. So, but one way is that I can go and assume that it is fully penetrated. So the question is that, and actually this is what we did to solve one of our homework problems, and we already talked about what do we mean here and what's going on in a system like this. But the questions that you may have is that you want to know what type of boundary, what type of rivers would act or be a good candidate to be considered as your boundary condition. You learned that there are 4 major rivers. If you would like to consider the interaction between the groundwater and surface water, there are almost 4 opportunities or 4 conditions that we need to think about. Our river would be a gaining stream like this. The water gets into the stream. The river would be a losing stream. It can be a disconnected stream where the groundwater is way below the stream bed, and in some special cases we have a through flow rivers, which from one bank the groundwater gets into the system and it gets out from the other system. But I want to now, at this point, I want to talk about the first A and B boundary conditions. So these are 2 types of rivers that we really like as a groundwater modeler, and I'm going to talk about the other 2 in next videos. But in these 2 rivers, for example, if it is a big major river like a Mississippi River, we consider that there is a huge and there is a big hydraulic connection between the aquifer here and the stream. Or in other words, in the literature you see that actually the river is well connected to the aquifer. So in this condition, and when this happens, for example, usually it depends to the so many things. For example, what are the thickness of the stream bed, what are the hydraulic conductivity of the stream bed, what is the thickness of the shallow aquifer that we are looking at. But in so many cases we can assume that the system is well connected, and in this case we usually consider a no flow boundary condition at the middle of the river. What does it mean? This might be a little bit confusing because we talked about the no flow boundary conditions where we have a very low hydraulic conductivities. But in this case, you know that we have a reasonably good hydraulic conductivity here, but we can put a no flow flow boundary condition here. So we are going to talk about this later on and look at this in another example, but I want to clarify why the no flow boundary condition is the best mathematical expression here. If you look at the flow direction here, so technically we assume that there is a vertical flow here. The groundwater gets into the bottom of the aquifer vertically here, and again here, but in the other direction, the groundwater gets into the system vertically here. So it means that the water cannot move horizontally, or if there is a streamline here, the streamline comes here and goes up like this. So this streamline cannot pass through this line. Okay, so it is a symmetric system, for example, here. So it does something like this. So this streamline cannot pass through this layer. So similar thing here. So the water gets in and does something like this. So this is my assumption. Okay, so this situation can be well represented by a no flow boundary condition here. So technically here I assume a no flow, I assume that there is a no flow boundary condition here, and I just, for example, go and solve this side of the model. Okay, and I put a no flow boundary condition here. Similarly, I put a no flow boundary condition, for example, here. So these are my all no flow boundary condition, and I want to model what is going on here. The water hits a no flow boundary condition and goes up. So this is one very interesting situation that we usually consider once we are dealing with streams. But again, you should be careful. I mean, this is not the only way to look at the problem. So this is just an example, but this is a very good example how we can simulate the interaction of the surface water and groundwater, which is very, very, very important. And I hope that actually you learned something new and interesting here. And we're going to work on similar examples, similar situations that actually I hope that you will see how we can go and convert this conceptual model into a mathematical form. If you remember that actually this is where we want to design a groundwater model. So the idea here is that we have a conceptual model and we would like to transfer it into a numerical model, right? So this is a very good example that I think it's worth spending time to talk more about it here. We are going to continue talking about different boundary conditions and sometimes advanced form of boundary conditions, including type 1, type 2, and type 3, specifically type 3 boundary conditions in next videos again. The fourth common physical boundary condition is the freshwater seawater interface. So as you see here in this picture, so this is sea and this is the fresh groundwater. So technically the groundwater moves like this and eventually hit a saltwater system like this. And as you see, essentially due to the density differences between the freshwater and saltwater, we always see a wedge So this is a very interesting field of study, actually. So this is a density-driven flow at which the salt water intrudes into under the land surface. But as you can guess, although the density there, for example, if the density of the water here is 1 gram per cubic centimeter, the density of salt water, if I'm not wrong, is something like this. So this small amount of only 2% difference makes a huge changes in the response of the groundwater flow. So in this system, so it is salt water and this is fresh water, and due to the density differences, technically these two different waters, they don't fully mix with each other except in the area which we call it the transition zone. Okay, so in the transition zone, you know that actually the water here, the water goes up and gets back during the night, the tidal effects, and also the situation here, we have a pumping well, so the groundwater head changes. So we always have an area where we have a mixture of salt water and fresh water. For example, the density here is 1.01, for example. So if this transition zone is stable, and if it is located almost in its place, we can consider this a boundary condition for our groundwater system. For example, if we would like to model this chunk of the system, for example, the freshwater side of the system, we can assume a no-flow boundary condition here and a specified boundary condition here, for example. Okay, so this is one way to look at this problem. But again, there are scientists and researchers when they look at this system all together, so they have both fresh and salt water, and they are interested to model how this wedges or the toes of this wedge moves. Okay, so or learn more about the transition zone. So, but this is one way to, the other way to look at the freshwater seawater interface. So these two are different diagrams of saltwater intrusion or freshwater saltwater interfaces. So we already talked about this situation where we have totally two different water flows. So I didn't talk about how the groundwater in the salty part moves. So technically the groundwater gets into the system, and it comes here and returns and comes back. So this is the general flow direction under the sea, and the fresh water comes like this and hit this denser water. It cannot intrude and eventually changes its direction and go and emerges here. So this is a one-layered system, but this situation can be even more complex and would have been occurred in a layered system like what you see here. Well, these were 4 common forms of physical boundary conditions that we as groundwater modelers trying to go and find and define the space domain of the problem based on those information. But the question, and very critical question here, would be what if there's no physical boundary around the perimeter of the problem? What we can do then? For example, in many urban type groundwater models, we usually we may ask to model a well field, for example, like this, but we know that there is no river or fault, or I don't know, a lake or ocean nearby the system that I can go and use to define the space or spatial domain of the model. So what we do in this situation, essentially, in this case, which happens a lot, we need to go ourselves, find a way and define or derive a proper boundary conditions for our model. Usually, we define the model, the hydraulic, but the location of the hydraulic boundary conditions based on two types of streamline or potentiometric lines information. We already talked about the streamline. If you remember, once we talked about the interaction between the rivers and the aquifers. We said that one way to look at this problem is that we go and define a groundwater divide at the river due to the form and shape of the streamline. Okay, so we already talked about this. So so you will see in the next slide, this is pretty much same idea, and we can practice this situation in the next slide. But the other relative and related information is the potentiometric line information, where we know how the head changes, and we're going to solve we're going to look at some examples and learn more about these two approaches. Okay, let's go and look at this interesting example. So here, assume that I'm asked to go and model the groundwater flow system in this site. You see here a river, but assume that this is a seasonal river and I cannot use this stream as a physical boundary condition for my conceptual model or numerical model. So what I would do here, I would go and study the potentiometric line maps or information. As you know, and as we learned in the hydrology classes, if we have a streamline, it doesn't matter, it's a surface runoff or it's a groundwater. So if we have a potentiometric lines like this, technically we can go, for example, assume that this is positive 30, positive 25 meter, and positive 20 meter. So if I go and assume, if I go and draw a perpendicular line between these potentiometric lines, technically I can go and define the streamlines. Okay, so streamlines are nothing but the streamlines are technically the path where water moves on. So, and you know that actually if we have a better or high resolution potentiometric lines, then we can go and actually draw better and more accurate streamlines. But anyway, using the streamlines, we know that we simply can go and find how the groundwater moves. So if we look at this example, we can go and define a no flow boundary condition here, here, and here. How? If we look at this, the streamlines, for example, this is -40. This is, for example, I don't know, I hope that I'm right. This is -35, -30, -25, and -20. So assume that actually -4 is the low hydraulic conductivity, 40 is low hydraulic head, and herein I can go, and if I want to look at how water moves, here I can go and draw a perpendicular line, and I can draw this line. So it means that the water moves like this. So I define a no flow boundary condition here because the water moves like this here. So the water, so there is no flow in this direction. So the water moves parallelly at this location like this. Okay, so that's why I define a no flow boundary condition here. Similarly here, if you go and see the streamlines is like this, or the other way, I don't know, based on the hydraulic head, and also again the streamline is either this way or that way, but the water does not move in this direction. So that's why I can consider a no flow boundary condition here, here, and here. Okay, so we are going to practice this concept I think in other examples, then things will get more clear. But this is one form of very typical no flow boundary condition that we can go and find and define. But there is one important thing that you need to be careful with. That is the fact that these no flow boundary conditions that we have found, they can move. What does it mean? If you go and find a potential map like this, you will see that there's a date on the map. For example, this is a 2005 potentiometric line. And if you go and find another map, you can go and find a 2010 potentiometric map. And as you can guess, these lines or potentiometric lines would not be the same in the 2010 years, right? So they may change, they move because the groundwater moves, right? So, but that is the thing that you need to think about once you want to define a no flow boundary condition for your system. But there are so many cases at which, although if you go and study multiple potentiometric maps in different years, and actually I'm going to show it later in the next slide, you see that actually they are reasonably located in a similar places, that actually you can make an average of these, for example, 3 no flow boundary conditions and define a proper boundary condition which represents the average condition of these 15 years. Okay, but definitely this is something that you need to be careful with. Okay, let's look at this example again. So we said that we can go and define a no flow boundary condition here based on the streamline information, right? So why I stopped here? Okay, why I didn't extend it to boundary or no flow boundary condition? So the answer is simple. If you look at this area, you see that actually there's a potentiometric line of -40 here. So it means that the head here, 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 and all points all across this line is -40. And you know what type of boundary condition suits this situation. It is nothing but the type 1 or specified boundary condition. right? So I can define, based on the potentiometric line itself, I can go and define a specified head boundary condition. Okay, so, and you know that actually you can go and interpolate, and if you need, you can go and find or interpolate the head distribution information. For example, if this is -40, this is -35, this will be -37.5 meter information, and you can go and actually use if you need. But again, the things that you need to be careful with is that, again, these potentiometric surfaces moves. For example, if this is an information for 2010, if you go and look at the 2015 map, for example, then you'll see that the -40 line is, for example, something like this. Okay, so it has been moved or shifted. So, which is highly possible because this is a transient system. This is the groundwater moves and everything changes. That's why these potentiometric lines surfaces also will change. But usually, as you see in the next slide, I guess, you see that usually we study the multiple years and make an average of what we see in multiple years and come up with a good approximation. So this is one way. This is the other piece of the boundary condition. If I want to highlight the no flow, so the reds are my no flow boundary condition, and I can go and define a specified boundary condition like this here and like this here. As you see, for some reasons the and also you can go, it doesn't mean that technically you can go and use a constant head. So you know that actually the head here is constant, the same as this, the same as this, the same as this, the same as this, okay? But the specified head does not necessarily mean that the head can be constant, right? So it means that you yourself can go and find how, I'm trying to find, let me use orange. So here, if the head, for example, I don't know, this number is -5, this is -5, so I assume this will be -10. If this is -10, it means that the head from here to here goes from -5 to -10, right? So it means that if I want to find the head here, that will be, for example, -7. Or -6. So you can go and interpolate and find these information. Similarly here, 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 here. So, but this is another form of a specified head. So technically this way you can close your loop and define a proper spatial domain where you can define a proper boundary conditions for. So, for example, if I was asked to go and model this area, I would go and talk with the client and say that, well, I mean, it's better we go and extend the groundwater model domain and map to this area, or find a way to find a closer boundary condition to our area of interest. This is another example of how we can define the physical boundary conditions or hydraulic boundary conditions for our problem. As you see here, again, based on the potentiometric map information, the modeler has gone and defined a no-flow boundary condition, which is shown by solid line. So this is a no-flow boundary conditions, and the dotted line or dashed lines are the specified head boundary condition. Okay, and again, as we discussed, for example, the purple line, the purple color shows both this the no flow and specified head boundary conditions in 2005. Okay, in 2007, the model has gone and studied the boundary condition, and if you go and find, yeah, this is the blue line, right? So you see that actually now the specified head and no flow boundary condition looks like this. So as you see, usually, at least in the small temporal domain, the groundwater boundary conditions are expected not to move significantly. So what we do, we can go, if you want to model a transient groundwater flow, it means that how the groundwater flows from 2005, for example, to 2015, we can go and make an average of this boundary conditions, I mean their locations, and define a boundary condition. For example, the black line shows almost the average allocation of these boundary conditions. So as we see, again, I want to repeat these two important things here. So we said that once we are defining our boundary condition, we need to think about the fact that the location of these boundary conditions doesn't matter, specified head or no flow boundary condition would change as times goes by. And the other thing is that, again, we already talked about this, is that once we are defining the specified head boundary condition, we need to be careful and think more about the limitation of this type of boundary condition. It's not a limitation, it's something that we need to be double check and think more about it. And that was nothing but the fact that the specified boundary conditions can absorb or discharge an infinite amount of water into our system, which may not be right. It means that actually the groundwater head here is always -40, no matter what is going on here, no matter how many pump wells I will put here. For example, if I want to design a well field. So this will always be -40, assuming that the outside world has enough water to pertain or keep the head here to -40 all the time, okay, which might not be very realistic. But these are two things that we need to think about. Okay, I will stop here and finish this video by showing you this interesting cartoon, hoping that you've learned new things in this session and you enjoyed learning more about